start today's lecture. Today we will be talking about machine translation. Okay. As always, I am most of the time I am using these slides from the Stanford NLP group, and this is okay. This is the overview. Okay. Machine translation, and machine translation is one of the important. Efkan, are you going to say something? Your hand is up. Just lower your hand if you don't. Efkan, are you there, Efkan?
I am here.
So you are raising your hand.
Okay, I will lower my hand.
Okay. So machine translation is one of the important areas of research in natural language processing. One of the complicated tasks of natural language processing. And we are going to look at the machine translation area, both in terms of statistical machine translation and neural machine translation. And while people are working on this problem, machine translation, they came up with a new idea of attention, and we are going to talk about attention. Attention is something important because again, it originated from the NLP research, but later people started using it in all other kinds of artificial intelligence problems, and we are going to look at the attention later at the end of this lecture. Okay, so let's look at this machine translation again. Okay, so machine translation is just simple in terms of definition. So if you are giving a sentence in another language, for example in French, and you are supposed to translate it to English or Turkish, that's the definition of it. So it is much easier to define than other NLP problems, but it is very tough area to work on. So as soon as, like we talked about it last time, as soon as people started talking about computers, artificial intelligence stuff, they started talking about translating between the languages, because they mostly, especially the newcomers to the area, they thought that translating from one language to another language is as simple as replacing the words. Okay. Well, we know that replacing the words from the dictionary is not a very good way of translating from one language to another language. You have the grammar, you have the phrases, you have the semantic mechanisms of different languages. So it is not that easy. So this kind of stuff, like rule-based stuff, if you say this, then this is that. If you see that, then this is that, did not work very well. And people soon learned it in 1950s that this is not a very trivial problem. This is a difficult problem to solve. Okay, so that's why they had to spend lots of time to deal with problem. So from 1960s to until 2020, we did not have very satisfying tools for the machine translation. So it took people, science community, engineering community, to come up with barely usable models of machine translation systems in the real world. So up to 1990s, all the systems were rule-based, and we know that rule-based systems have many limitations, and we talked about those limitations when we talked about the part of speech tagging and etc. So they started using this statistical machine translation or machine learning stuff. Okay, so the core idea is this: develop a probabilistic model from data. Okay, that means that if you have the data, okay, if you have the data between French and English, we have such data. For example, the Canadian Parliament, there are two official languages in Canada. One is French and one is English, and all the Parliament documentation, they all have to be kept in two different languages. Okay, the same things, all the law and all the correspondence, all the speech made in the Parliament, in Canadian Parliament, they are all recorded in French and English. So that means what? That means we have a parallel corpora, okay, between two languages. Some newspapers, they are printed in both in English and some other language, like some Arabic newspapers. So we have those too. So suppose we have such a data, okay, such data set, and we like to develop a model, probabilistic model between these two languages. This is what I like to do. We want to find the best English sentence while given the French sentence. You are given the French sentence. Let's say I have maybe maybe 10, 15 words in this sentence. I like to express the same sentence in English. Given the French sentence, what is the probability of having this English sentence? And let's develop a probabilistic model for this representation. Then after that, I can search in this space, in this white space or the English space that maximizes this probability. Okay, so that's what we are going to do. But calculating this probability is very difficult. Okay, so instead of calculating this probability, maybe I can, again, as always, use the bias rule to invert this formula into this one. Okay, we know that this one and this one are equivalent, right, from the bias rule. That's what we are going to do, and that's we do. Previously, we do this inversion for one purpose. Do you guys remember why we use this inversion? Previously, I used to say things like, we do this inversion because calculating this invert is easier than calculating that. Do you remember why we do that? We do that inversion for one purpose.
Calculating the inverted version is easier than the other.
Yeah, but why is it easier? Why was it easy? In this case, it is not easier. I mean, converting from French to English, English to French is the same thing. But in this case, it is not valid. But for the other cases, it was easier because usually we have things like, okay, we have things like, okay, we have the given the observations, what is the probability of the cause? Okay, that was the thing. Just a minute, I'm sorry. Efendim, buyurun. Evet, yerindeyim. Bilgisayar mühendisliği 204 numaralı oda. Efendim? Gebze Teknik Üniversitesi Bilgisayar Mühendisliği. Siz neredesiniz? Ben Gebze Teknik Üniversitesi Bilgisayar Mühendisliği bölümündeyim. Allah Allah ya, benim adresim standart N11 değil mi bu? Ya bilmiyorum, ben adresimi söylüyorum, eğer geri gidecekse gidecektir ama yani adresim bu. Peki, oldu. Teşekkürler, güle güle. Usually I have the observations and probability of this cause. That's what we do. For example, the examples we gave were like, if I see somebody has a fever, right? High fever, coughing, tiredness, okay? And what is the probability of this person having COVID virus? Okay? So we didn't like it because calculating this difficult. Instead, we said that let's calculate this one. What is the probability of a person having given that person has this COVID virus, okay, what is the probability that this person has fever, right? This is easy to calculate because all the books, all the research articles, they give you this probability. COVID causes fever in 85% of the people, right? So that was the reason. So I just converted from the cause to the observation, cause to the effect. So cause effect probabilities are easier to calculate, but in this case, I don't have it, okay? This is French to English, this is English to French, but this one is nice, okay? This one is what is this? This is our language model, right? We already did this, okay? I can develop a nice language model for English or French or Turkish. We did that in our homework and in our examples, right? So if I divide this problem into two, one is this probabilistic model, the other one is the language model, then it is easier than this problem because at least I can handle this part. At least I can handle this part, and it is logical too. Look at this one. Argmax y py. Okay, argmax y py. What does that mean? It means find such a sentence y that makes this probability and this probability maximum. That means what? That sentence should be probabilistically high in terms of that language model. So whatever you are producing, it should be high probability sentence in this model. Okay, so that's a good idea to make this inversion. Okay, to make this inversion. Still, this is a tough problem. But at least we can handle this part, and maybe even if we make some mistakes in here, at least the sentences that we are producing would be grammatically correct, and they would obey the rules of the language model. Okay, so that's what we are going to do. Okay, so with the statistical machine translation, we need the parallel data. As I said, the parallel data is available for some places. The same book written in two different languages, we know that. The same, for example, the movies, right? When you take a movie, when you look at the closed caption data, closed caption data of the movies, it is available for Turkish and English and French and etc. And this goes as far as like 2,000-3,000 years ago. This Rosetta Stone, I think it was written maybe 2,000 years ago, maybe even more. The same agreement between Egyptians and maybe Greeks or maybe Romans, I don't know. is written on the same stone in two different languages. These two are Egyptian language. This is Greek. Okay, so this is kind of a form of parallel corpora. Okay, so these kind of things are available. I can use them. Okay, one thing that we do most of the time to make this easier to calculate. Okay, this is a very difficult one. Okay, to make this easier to calculate, I will assume a alignment. Okay, what is an alignment? Alignment is this. Okay, it's a mapping between the source sentence and the target sentence. For example, this is the alignment. The first word corresponds to the first word. This is the German sentence. This is the English sentence. Morgen in German, tomorrow in English. Fliege will fly. So this word corresponds to two words in English. Ich is I, and nach Canada in Canada, etc. So these two words correspond to these three words. So this alignment is a function. So instead of estimating this probability directly, I introduced this latent variable. Remember, we introduced the latent variable for the part of speech tags. Now I introduced this latent variable. This latent variable alignment will tell us the ordering change of the words between two languages given this sentence. Okay, given this sentence in German. Okay, so give me the alignment and the corresponding English sentence. Okay, so alignment is a separate problem. It is not as difficult as the machine translation problem. It is a sub-problem of it. If we can solve alignment, then maybe I can solve this corresponding translation problem between the words, and that will make my job a lot easier. But as I said, alignment is easier than the translation problem. It is not as easy, very, very easy problem because sometimes, for example, between English and French, between English and French, so Japan shaken by two new quakes, and the French corresponding French sentences here. Some of the words are not there in the other sentence, right? So this one, so it looks like the French people, they put this article at the beginning of the country names, right? So in English they don't. So it is just missing. So there is no alignment. There is no corresponding word for the other one. It is just null. And the same thing happens between Turkish and English too, because in Turkish we don't have the articles, right? In Turkish we don't have the articles. Sometimes the same word, I mean, for a single Turkish word, you have to say many English words. Like, for example, kitapları. When you say kitapları, the English word would be their books, right? So I have to say their books. So I have to do that kind of alignment too. So the alignment is not an easy problem. Sometimes it is gone. Okay, for example, the book. When you say the book in English, in Turkish it is kitap, right? So, or maybe kitabı. The is gone. Okay, sometimes it is many to one. Okay, like this one. So these three will correspond to this word only. Sometimes it is one to many, right? So this implemented will correspond to these three words. Okay, like that. I mean, some languages have very specialized words for some specialized cases. For example, for some reason in English, in French, sorry, there is a separate word for hit with a pie. Hit a pie. So there is a word for it. There is a verb for that action. And English, obviously, in English, obviously, there is no such word. And in Turkish, I don't think that we have such a word. Hitting someone with a pie. Okay? So those are the alignment problems. And alignment is complex. Okay? Many-to-many is difficult. Okay? The poor don't have any money. Okay? These 4 words correspond to these 2 words. So the phrases to phrases is even more making it even more complex. Okay? So how do we learn the alignment for statistical machine translation? Again, it's a different problem. We learn as a combination of many factors. Probability of particle words alignment. Okay? So it is how do you well, remember there are languages that does this subject, object, verb. There are some subject, verb, object, etc. So English is I go to school, subject, verb, object. Turkish is ben okula giderim, subject, object, verb, right? Ben okula giderim, ben okula gittim. So when you do the alignment between languages like that, okay, if the type of the language is similar, is the same, then usually your alignment is close there, like that. Okay, this one, that, and maybe that one and that one, like this. So it is almost the same. But if the languages are very different, their subjects are maybe at the beginning, but if the verbs are doing that, okay, so it depends where you are on in the sentence position. Okay, so the probability of particle words aligning, okay, probability of particle words having particular fertility, okay, number of corresponding words, etc. So you need to know that. And the alignments are latent variables, okay, and they are explicitly specified in the data. Somebody has to go sit down and calculate it or mark those alignment data too. Okay. So even if you have this problem, even if you solve that problem, okay, even if you solve that problem, calculating, I mean, let's say I know this one. Given the French sentence, what is the corresponding given this French sentence, give me the probability for this corresponding English sentence. Even if I can calculate this probability, calculating this argmax y is difficult. It is too expensive. Why? You need to scan, you need to iterate over all possible English sentences to calculate this maximal probability. Okay? So that's a very difficult question to answer. What is the sentence that makes this probability maximum? Okay, enumerating all possible y is not an answer. Okay, so like we did before, we tried that before. So we are going to assume independence assumptions, like we did with the language modeling. Okay, so we are going to assume more constraints like those, which will make our model a little bit weaker, a little bit less realistic, but that's what we can do, and we are going to do it. And using things like the dynamic programming, like the Viterbi algorithm and other types of dynamic programming, we can decode this problem up to some point. So that was the basic idea of the whole statistical machine translation. Okay, so you know this decoding with dynamic programming, right? So I can say, okay, from words are from 1 to L, and I'm doing this one by one, maybe with the alignment and everything. Okay, I can consider both the alignment and the probabilities, and I can decode it from phase to phase. So, but this way I have to assume lots of independence assumptions like the Markov assumption, etc. Okay, so uh, we are not going to talk much about it, but it can be done. So that was it. So from 1990s to 2010s, before the deep learning or neural machine modeling, neural machine translation took over, it was a statistical machine translation was a huge research field. Okay, the best systems were extremely complex, and they weren't that successful either. If you remember, maybe 5 years ago, 6 years ago, the Google Translate used to produce lots of funny stuff for your sentences. Everybody used to laugh at them. Sometimes I mean, the words that they choose sometimes are good. I mean, as a starting point, they were good, but the sentences they produced, they didn't make much sense most of the time, and sometimes they were funny. Okay, they were extremely complex, and the results they produced is not good. Okay, and you had to solve lots of subcomponents like the alignment problem and lots of things. You need to know about the language, both of the languages very well, both French and English, or both Turkish and English, because you like to extract some features. You have to do lots of feature engineering. Okay, and you need to require compile and maintaining extra resources. For example, I have a phrase in Turkish, and I have another phrase in um, okay. For example, the English, the British say it is raining. It's raining cats and dogs. Just to say that it is raining a lot. In Turkish, we say deli gibi yağmur yağıyor. So it's kind of the corresponding phrases between these two languages. So you don't want to translate them literally. You don't say in Turkish kedi köpek gibi yağıyor. Well, we don't say that. That sounds funny. Okay, so you need to compile and maintain these kind of tables. Okay, and you need lots of human effort. That human effort means that we are open to mistakes and etc. So lots of work done on this field, but at the end we didn't come to very good conclusions. Then we started doing this neural machine translation. So what did we do with the neural machine translation? Okay, a, a single neural network, it will take the source language sentence, and it produces the target language sentence. Okay, so to do this, we design networks like sequence to sequence network or sec to sec. Okay, and it involves two RNNs or two LSTMs. This is how it is done. Neural machine translation. There is an encoder network. Okay, there is an encoder network. We give the source input, okay, the French input, 1, 2, 3, 4 words to this encoder network. Encoder network takes this in, okay, it doesn't produce any output, okay. After the last word, we input, okay, after the last word, I take the RNN's internal representation, internal state, and I feed this internal state to a decoder network. And I put this word start, a special word, and this one starts producing the corresponding English words one by one. First it produces he, I take this he and feed in here, and hit is taken here and feed in here, It goes that way. So it produces he hit me with a pie. So this is the encoder network, this is the decoder network. Their parameters are different. These are called encoder decoder structures, and they're based on RNNs and LSTMs. Okay, RNNs and LSTMs, and they are trained this way. You provide the input here, and you expect to get the output there. If the output is different from what we expect, then that increases the loss. So what do we learn here? We learn the weights of the encoder network and weights of the decoder network. Okay, so it turns out that this symbol structure works better than all those okay 30 years of statistical machine translation work. Okay, and the nice thing is, what is the nicest thing about this picture compared to statistical machine translation? Question for you. Tell me the nicest thing about this picture compared to statistical machine translation.
Any length of input can be considered in theory.
Well, that's a good feature, but I can have the same thing with the statistical machine translation too, because remember, we try to calculate, given the French sentence, what is the corresponding English sentence. Both of these sentences could be different length input and output. So I have the same advantage in the...
Must be static. Yeah, I mean, different. You may say you may adjust it to be bigger, but it must be static in a model. Here it is not static. Not static frame length.
No, well, it is not. It's not static either. I mean, remember, I can do this. I mean, what is the probability in Turkish, a Turkish language model? Ben okul git. Okay, I can calculate the probability of this sentence in Turkish. It's not going to be that high, but it doesn't matter if I have 3 words or 5 words or 8 words. These probabilities can be calculated for any length of sentences. So the same thing is here for two. So the length of the sentences, for English it could be different, and for French it could be different. Doesn't matter. That's an advantage, but I mean, I have the same advantage for the statistical machine translation. There is something different. Okay, let's go back. Let's look at this one again. Okay. So these are the problems with the statistical machine translation. Which ones are gone? Well, the first one, for example, extremely complex. The network that I showed you is not complex. It is not extremely complex, right? It's a simple encoder decoder 2 networks. Okay. We have separately designed subcomponents, but we don't have many of them. Maybe the most important one is this one, feature engineering. Okay. You don't have to know English or French to optimize that network. Okay. All you need is the data. If you have the data, enough data, okay, you don't have to do the lots of feature engineering, okay, and you don't have to do this maintaining of equivalent phrases and anything like that, okay, and you don't need much human effort. So this one, they are all handled kind of with this kind of an approach. It's a much simpler approach. it doesn't include, it doesn't have, it doesn't contain those problems that are inherent with the statistical machine translation. That's why we like this system a lot. If it works, then we should be fine. And basically, up to last year, maybe 2 years ago, Google Translate worked this way. Nowadays, they are using a little bit something different based on the attention. Okay, let's move on. Okay, the sequence idea is very useful actually. It can be used in many places. Okay, for example, in summarization, you give the original sentence here, you get the summary from the other part. It works. It works very well. Okay, dialogue. Okay, you know the dialogue system. You ask a question to the bot. Okay, a chat bot. You get the result from the other one. You say that okay, you dial in and you ask your automated answering machine, okay, what is my balance in my account? And it says that you have this many Turkish liras in your account. Okay, you ask a question. So the what? Okay, when you say, okay Google, how is the weather tomorrow in my hometown? And it gives you an answer like that, right? So, question answering system, okay, dialogue system, parsing systems work very well. Okay, for example, you say that okay, I am giving you this, so produce me part of speech tagging. Okay, this is a noun, verb, adjective, verb, etc. Okay, so you get those two. So this sequence to sequence models are very popular. They are used very widely in many places. And one of them is the neural machine translation, as I said before. Okay, good. So let's look at this neural machine translation again. It's a conditional, okay. Sequence to sequence model is an example of a conditional language model. What do we say conditional language model? Because we are trying to directly calculate this one, okay? It is conditional because its predictions are also conditioned on the source sentence X. This one tries to assign probabilities to Y. Y is the target language, right? But whatever we are doing, it is conditioned on the input sentence X. So this one includes both this conditional probability, also it includes the language model too. Okay, so that's a nice feature. So how do we train the neural machine translation systems like the statistical systems? We get a big parallel corpus. Okay, and this is what we do. If I know that this sentence corresponds to this sentence, okay, this sentence corresponds to this sentence. So when I say start, it should give me a he. When I give me a me here, it should give me a with. Okay, if whatever this one produces is different than he or with or and here, then that will increase my loss function, right? That will increase my loss value. If my loss value is increased, then I will take that the gradient of this value with respect to the parameters here, the weights here, also the parameters there, okay, with respect to those. So at the end, my gradient descent will find me the weights of this decoder part and the weights of the encoder part, and that will be my translation system. So my sequence-to-sequence system is optimized as a single system, and the backpropagation operates end-to-end. As you see, all I am doing is comparing the words and their present representations. I am not talking about feature engineering. I am not talking about the phrases. I am not talking about the alignment problem at all, right? So that's it. That's the whole thing. That's the whole thing. We train a neural machine translation system. This way it is training a regular neural network, or at least a regular RNN. Okay, so that's why we like this kind of a solution. That's why we like this kind of a solution. Okay, when we run this, when we have trained the system, somehow we trained it. We have the weights for this encoder and the decoder part. We have both of them. So what do? We run it, right? We give the input sentence, and we try to produce the output sentence. Okay, when we produce the output sentence, okay, we don't, okay, so when we say start, it produces an he. I give he here, and it produces an hit. I give hit here, it produces a me, and etc. This is called greedy decoding. Okay, this is called greedy decoding, and we don't like greedy decoding much. Why? Because can anybody tell me why we don't like greedy decoding much? Taking the, okay, this is argmax, right? So out of all the words in my dictionary, he is the maximum probability word. I take it and I feed he here and hit produced, and I take hit here and me is produced. But taking the maximum probability word at each step might have some problems. What is the problem?
There may be other possibilities. You start with start and you predict he.
Yeah.
But
maybe, well, I mean, yeah, exactly. I mean, instead of he, let's say this one says that he has the highest probability. The next probability is for she, maybe. She has a slightly lower probability, but if I choose she instead of he, maybe the next one will be a higher probability verb, right? I don't know. So that's why it is called greedy decoding, and we don't like greedy decoding, but it's a good one. But we can do better than the greedy decoding. Maybe I should consider second best probability, third best probability, fourth, fifth, and etc. So don't put all the eggs in one basket. Okay, don't try to use the greedy decoding all the time. Try to consider the other possibilities too. That's what we are going to do. Okay, so here's one example. This guy says that, okay, for example, if I produce he at the beginning, he has the highest probability, then hit another highest probability, then another highest probability, but I cannot produce the next one is going to be maybe a very low probability one. Maybe I should go back and produce another one, the next high probability, but I cannot go back. That's the problem with the greedy decoding. So what are we gonna do? We are going to do, okay, some clever stuff. But whatever we do, I can't do the exhaustive search. What is exhaustive search? Exhaustive search is this. Okay. For this one, get all the possibilities of 40,000 words in my dictionary. Then the 40,000 words in my dictionary, 40,000 words in my dictionary, and multiply their probabilities. Whatever produces the highest probability, take that one. That would be a very nice solution, but that would be too expensive, because 40,000 to the power of 1, 2, 3, 4, 5, 6, 7 is a very big number. I can't exhaustively test everything. Okay, exhaustive search decoding is not possible in this case. Okay, it is far too expensive, and obviously for Turkish it is not possible either, because for each word I have 40,000 times 10,000, because each word can have more than 5,000 forms, for especially for the nouns. That's not good, so I am not going to do that. Instead, I am going to do this beam search. Okay, does anybody know what beam search is? Maybe from other courses like the heuristic optimization, maybe algorithm course. Beam search. Can anybody tell me what beam search is? It's an artificial AI technique doing for optimization. As it says, it is not guaranteed to find the optimal solution. It is not as perfect as optimal exhaustive search, but it is much more efficient. We are going to use it. Okay, so maybe I should take 10 minutes of break because our time is up. When we start at 14:30, I will ask you about this beam search again. Okay, 10 minutes. Okay, we are back. So we are going to use beam search. Did anybody has an answer for the beam search? Did anybody remember it? Okay, no answers. Okay. Beam search is this. Instead of going for the best performing one, like this one, what is the best word he, what is the best word hit, etc., we keep 4 or 5 best solutions. Okay. What is the best other than he, she, I, etc.? Then we continue. What is the best 5 sentence that I can continue, etc.? That's the idea with the beam search. Okay. On each step of decoder, keep track of the k most probable partial translations. Okay. And for each step, calculate this score. So what is the score? Score is the from 1 to t, calculate given all these input sentences and whatever I produce, what is the probability of next word. Okay, so the score, because probabilities are between 0 and 1, the logarithm, remember the logarithm function? Remember the logarithm function? This is e, right? E to the power x, and this is logarithm of x. Logarithm of x. So this is like 1.0, this one. So between 0 and 1, logarithm of probability, that means that they are all negative, right? So these numbers are all negative. When you add them up, they will be all negative. Scores are all negative, and higher scores is better. Okay, higher scores are better. So we search for high scoring hypotheses. Okay, we search for high scoring hypotheses and we keep top k on each step. Okay, we type k on each step. Of course, beam search is a heuristic approach, but it is much more efficient than exhaustive search. Okay, it is much more efficient than exhaustive search. Let's see an example actually. Let's say, okay, I gave this one start to my decoder, and my decoder says that, okay, I can give you this. There is this he and I. Okay, in this case, I am using the beam size is K2. Remember I said 5? Just to keep the things a little bit simpler, I said K is 2. So I am going to look at the 2 alternatives all the time. Okay, 2 alternatives all the time. So higher the number, better. So in this case, given start, what is the probability of he according to this language model? Okay, it is he is better, but I am going to keep I around 2. Then I will continue, and I will say, if I am using he, what would be the highest probability words after he? It could be either hit or struck. After that, it would be was or got. Okay, so what is the probability of this line and this line, this line and this line? Okay, so 4 of them. It looks like here I have this one. Oh, sorry. Okay, I have these numbers. I have this one, this one, this one, and this one. It looks like the smallest ones are like this one and this one, right? Okay, we need to be close to 0. 0 is the best because probability of 1.0 is 0. Okay, probability, the probability 1 is the highest, the logarithm of that one is 0, that's why. Okay, so I am keeping this one and this one. So he hit and I was are the 2 possibilities that I'm going to pursue. So again, for K2, I will get 2 of them here, 2 of them there, and A, me, hit and struck, and calculate all of them, and these are my numbers, 28, 25, 29. Okay, so which ones are good? 25 and 28. Okay, so I will discard this part and I will keep going there. So he hit me or he hit A, and it goes that way. Okay, so again, at this one, so I am keeping 2 paths open. Out of 2 paths, I need to compare their next 2 successors. So that makes 2 times 2, 4 possibilities. And looking at these, it looks like this one and this one, right? He hit me with a pi, and he hit me with a width. He hit me pi, he hit me width. Okay, 2 of them, and I will continue, and it looks like in this case A and 1. Okay, at the end I am going to finish up with this one, okay, because at the end this is the smallest one. He hit me with a pi is the smallest one. This is the top scoring hypothesis. Okay, so with the K of 2 beam search, this is how I do. With the Viterbi search, okay, or dynamic programming search that we did before, the things were optimal, but in our case I don't do that. I just do the beam search, and beam search produces good enough results, and I am not doing the greedy kind of decoding. It is a little bit greedy, a little bit better than greedy, but it is not as good as the exhaustive search. But exhaustive search is too expensive. Okay, good. Any questions? If there are no questions, I will continue then. Okay. So one thing is that this, okay, since I keep adding all these numbers, if my sentence is longer, these numbers will get, okay, smaller and smaller and smaller. Okay, so it would be a little bit unfair to the long sentences, because this one will favor the short sentences, because short sentences, those numbers will not add to very small numbers. Okay, so how do I solve this problem? Okay, we solve this problem by okay, normalizing each possible sentence by its length. Okay, by their length. So what does that mean? If my sentence is t words long, just divide it by t. That's it. So your sentence being short or long will not have any advantage or disadvantage for you. Okay, so for the beam search decoding, you could use this normalization. Okay, so that's the basics of this neural machine translation. Okay, compared to statistical machine translation, it has lots of advantages, better performance. Okay, our results come back much better, more fluent. Okay, it uses better use of context, better use of phrase similarities. Okay, by the way, I mean, we don't do any of these explicitly. Okay, our encoder decoder network handle these, solve this automatically. We don't do anything. I mean, we don't have any phrase data set. We don't have any calculations for the context. Okay, these are all done implicitly by our network. Okay, so we have a single neural network to be optimized end to end. You don't have to know about the grammar rules. You don't have to know about the phrase rules of the language. Okay, no subcomponents. Okay, no subcomponents will be optimized, and our human engineering effort is much less than the statistical machine translation. Why? Because all you need is the parallel corpora, sentence by sentence corpora, and that will be it. Okay, no feature engineering required, and it is the same method for all language pairs. Okay, doesn't matter English, French, it is all the same thing. Good. Okay, so that's the neural machine translation. And the disadvantages of it, of course, there are some disadvantages. Nothing is error proof. All kind of techniques have some disadvantages. Neural machine translation is hard to debug. Sometimes it produces very stupid results, and you don't know what's going on really. You don't know really what's going on, and it is very difficult to control. Okay, because in the other case you have the rules or set of rules. If something goes bad, you know why it went bad. Okay, for example, if your alignment is wrong, you can easily see that your alignment is wrong. In this case, you don't have any clue. It just produces something. You don't know why it is producing it. It's probably the data or something else we don't know. And there is not easy. I mean, the result is we don't know how to fix that problem. And sometimes it's the safety concerns. Okay, if you don't know what kind of errors you are going to make with your system, I cannot use the system in safety critical applications because I don't know the limits of it. Usually it does very well. Okay, usually it does very well, but sometimes if it goes bad, if it goes nuts, then I mean there is nothing you can do about it. So that's why some people don't like these kind of systems. They say that I am going to use a statistical machine translation system, even though its performance is bad, worse than the neural machine translation system. At least I know what kind of errors it's going to do. Okay, so those are the disadvantages. Okay, so one question here is this: how do we evaluate the machine translation? How do we know that we are doing good? Okay, how do we know that we are doing this good? So there is no perfect method to measure your performance, but there are some widely accepted techniques. One of them is this bilingual evaluation under study, blue scores. It's not blue, like E and U are like switch places, but we read them as blue anyway. Okay, blue compares a machine written translation to one or more human written translations. Okay, and computes the similarity score. It's like the it's like the engram calculation. Okay, so when you say I go to school, and Turkish version is ben okula giderim, or you say okula giderim. Okay, well, I can translate it this way or that way. So how do you for example, the human translated it this way. This is the human translation, this is the computer translation. How do you compare these two sentences? So you take this 1 gram comparison. Okay, this is 1 gram, 1 gram, 1 gram. How many 1 grams are overlapping? 1, 2, 1 grams are overlapping. How about the 2 grams? Do you see ben okula in the Turkish sentence? No. Okula giderim, you say it? Yeah, I say it. So there is one overlap with the 2 grams and 3 grams and etc. So this is n-gram precision, and that's the overlap. And we don't like too short system translations, because when you make the translation too short, then whatever it produces is an overlap. That's not going to be good. So that's the basic calculation of the blue actually. 1 gram, 2 gram, 3 gram overlaps, and you don't want your translation to be too short. It's useful, but it is not perfect. Okay, because which one is the more correct one? Ben okula giderim, or okula giderim, or okula gidiyorum. Okay, usually maybe sabahları okula erken giderim, sabahları okula giderim. I don't know. Sometimes we say this, sometimes we said this. I mean, the fact that there is no perfect overlap between these two doesn't mean that our computer produced a bad sentence, right? So that's why we say that there are many valid ways to translate a sentence. Okay, so a good translation can produce a poor blue score because I didn't use the correct parameters for the test and etc. So usually, I mean, better blue scores, okay, scores of high scores of blue scores are usually good, but if they are very close to each other, for example, one blue score is 31, the other one is 30, we cannot definitely say that 31 is better than 30 because these kind of problems always exist, especially if your data is not very big. Okay, so let's look at this again, the progress of the machine translation, over time when we compare them in terms of neural machine translation or the phrase-based machine translation. Okay, so this is rule-based stuff. Okay, the blue ones, and the phrase-based stuff. Okay, so this neural machine translation actually started like 5 years ago, and as you see, these are the blue scores. Okay, these are the blue scores. As you see, in just 2 years, it took off. You might think that because it is new, of course, you might expect things are going to be better in just 2 years. Let's see what happens in the next year. But this trend continued. Now we are talking about blue scores around 30. Okay, for the neural machine translation systems. Okay, and this slide is very interesting actually. Okay, so in 2014, okay, scientists published their first sequence-to-sequence machine translation systems. Okay, sequence-to-sequence neural machine translation systems. Okay, so that means that that's the initial idea. In just 2 years, the sequence-to-sequence became the best performing commercial machine translation system. That has never occurred before in machine in 60 years of machine translation literature. Okay, it is simply amazing. So if this happens, everybody just they trashed all of their work of the last 40-50 years of machine translation, classical machine translation. Everybody started working on these neural machine translation system. Okay, so hundreds of engineers, hundreds of PhDs doing some work, and in just 2 years, okay, a few engineers and scientists in a few months, they were able to surpass their performances. That was amazing. Okay, so does that mean that we solved everything? No, of course. There are many problems with the machine translation systems. Okay, so the human translation is still way better than machine translation. Not all the time, but nowadays this is how the human translators work. They give the source sentence to these machine translation systems, and whatever they get, they modify those sentences. Okay, so they use them as a tool to give them ideas, then modify these sentences. Okay, so those are the kind of techniques that we use. this problem, maintaining context over longer text. Okay, this neural machine translation systems. I mean, we talked about the long, short-term memory systems. Nowadays, they are using the attention mechanisms or transformer-based networks, but still, we cannot address this longer text context problem. What is it? For example, you have a paragraph that starts with Ayşe in Turkish sentence, okay? Ayşe okumayı çok severdi, okay? And I am talking about Ayşe now. She did this and this and this and etc. 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 At the end, okay? Bir gün annesi ona şunu söyledi. At the end of the paragraph, for example, what is the reference point of O? We are talking about Ayşe here, right? But I told her name at the beginning of the paragraph. After maybe 10 lines of text, I didn't give her name exactly. When I translate this, I am supposed to remember her name, right? Even though I did not use her name, Ayşe, for a long time. So that's the maintaining context over longer text. So this machine translation systems are usually not doing this very well yet, but they are making progress. Okay, so we already know this, right? So it looks like in Spanish, it looks like there is a phrase for this. My friend has no hair on the tongue. It means, I guess, my friend talks too much without thinking, right? I think that's what it says. Okay, so if you translate these kind of phrases directly, it sounds funny. How about this one? When Shyam came to know that he failed the exam, his face went down. Well, his face went down is funny in English, but yüzü dökülüyor is not funny in Turkish. It's a very frequently used phrase in Turkish. But so these kind of things, common sense, idioms, phrases are difficult to translate. Sometimes this makes a lot of problem, and we don't know how to solve this actually. Okay, in Turkish we don't have the gender, right? In Turkish language we don't have the gender. When you say she works as a nurse, in Turkish we say hemşire olarak çalışıyor. He works as a programmer, we say programcı olarak çalışıyor. Okay, but when you translate this to English, you have to say either she or he. Okay, so how am I gonna translate this? I mean, should I prefer she or he? If the context is not there, I have to make up something. Usually, the machine translation systems, okay, they are biased with usually the nurses are females, and usually, unfortunately, the programmers are males. Okay, so when you do this kind of translation, you have these kind of biases because it comes from the training data. Okay, so, and sometimes we get stupid stuff like this. You put these kind of nonsense words in it, and it shows you out a nicely grammatically correct sentence out. Because remember, we are doing this, okay? Probability of given sentence X. What is the corresponding sentence in other language? So this language, this Y has to obey the rules of the language, Y. So it has to obey the rules of the language model. Okay? It doesn't check if this sentence obeys the rules of the input model. So it takes this kind of stuff. Of course, these are like a few years old. How old is this? I think this is 2019. or 2020, I don't remember. So they keep working on these, but you don't expect that these kind of stuff will stop from occurring. They will occur less often, might be, but they will be there. We don't have perfect solutions for those. Okay, so any questions so far? Neural machine translation. Okay, if there are no questions, then I will continue with the latest popular technique in machine translation or NLP or the general artificial intelligence deep learning stuff, attention. Okay, so the idea of attention is very simple, but it is very, very effective, especially with the sequential data like the videos or the sentences. Okay, and let's look at this one. Okay, while people are working on this sequence to sequence machine translation system, they invented this idea of attention. Okay, let's look at what this attention is. We know this one, right? The main problem, one of the main problems of this structure is this. Okay, there is this bottleneck. Okay, I learned this sentence. Okay, I learned this sentence. I input them to my network one by one, and the internal state of this encoder part becomes the input to my decoder part. So I have to encode all the information about this sentence in a single vector. Some people say that, well, this is not good. Some people say that this is not good. Why do I have to put all that data in a single vector? So, well, you might say that make this vector larger, but it's no solution for arbitrary length data, right? Okay, this vector keeps all the word information in it. Also, it keeps the ordering of the word information, etc. That's not going to be good. Okay, that's called the bottleneck, information bottleneck, and we need to find a solution for that. So somebody invented this. Attention provides the solution. So the core idea is this: on each step of the decoder, okay, during the training time, use direct connections to the encoder. Focus on a particular part. Okay, and it turns out that that's a very nice idea. While I am producing these, okay, always try to compare them with my internal state during the encoding. Okay, it is important to know which vectors are similar. Am I similar to this? Am I similar to that? Am I similar to that? Or am I similar to that? Which one is more similar, then I am paying more attention to that part. For example, when I am producing he during the training, I will see that I am paying more attention to this part. Okay, at the beginning. So this one keeps attention in the picture, and when I am producing this sentence, attention is always a factor. Okay, so let's look at this one. So how do you do that? Okay, this is dot product. Okay, remember, this is encoder, this is decoder. They are two separate networks. Their weights are different. Okay, their weights of the RNNs are different, but the size of this vector and the size of this vector, internal states, are the same. I can use a dot product to measure their similarities. If these two vectors are similar, their dot products will be high. If they are not similar, their dot products will be small. So I compare this one with all of them. one by one. Okay, and I get this distribution, attention distribution. These are the attention scores, this is the attention distribution. And I can run a softmax on it, okay, to make the total attention score, 1.0, but the distribution is like that. So while I am producing this, my attention is around there. I know that one. So maybe I could use this information to produce my first, okay, this is my attention output. Take your attention output, and feed that information to my network to produce this first word he, okay, and do the same thing with the second word. Get the attention words out and do it and put it in this vector form and use it in my network to produce this head. Okay, so continue that way while I am training this network. So while I'm training, the only information I get from the encoder part is not this bottleneck information anymore. I am measuring my attention with the input words and decoder structure, encoder structure. Okay, so there is more connection. More connection means that bottleneck problem is mostly addressed, and this longer dependencies, for example, this one is dependent on at the beginning of the sentence, is possible now because every time I am measuring this attention with the previous ones. Okay, that's called the attention. That's called the attention, and it turns out that this works very well. Okay, some people realize that this sequence with attention works very well, and they said that why don't we use this idea for everything? Why do we have to use these RNNs or LSTMs or convolutions or that kind of stuff? So let's do everything with attention. So they invented these transformer networks. Okay, these networks do everything based on this attention idea of the attention, and it looks like it is doing much better than anything that we have seen. So for the last 2-3 years, everything became attention now. All the video people, video analysis, for example, action recognition people, all the object detection people, all the natural language people, signal people, they all started doing stuff with the attention, and attention is our main tool right now. And remember I told you about the LSTMs and RNNs. They are almost dead for the current time. I don't know if we are going to revisit them again in next year or the other year. We don't know. They may come back with some new additions, but it looks like attention is becoming everything. And in fact, the people who first argued this attention is all you need. Okay, attention is all you need. Let's go to the Google Scholar entry for that one. Okay, it is a 2017 paper. Okay, it's a Google paper. It was cited 33,000 times. Okay, so it is like 5-year-old paper, 4-year-old paper, right? So it is changing everything. So many people are claiming that really. But see this one? Attention is indeed all you need. Okay. So we are doing that. Let me see what kind of, okay, among all the cited papers, and there is this one, and BERT is a, okay, BERT is a word representation technique like word2vec, but it is based on attention. Okay, it is using the bidirectional transformers. Okay, oh no, I don't want that. I don't open it. Bidirectional transformers, like the bidirectional LSTM stuff. And the idea is this actually. I know that where did it go? Let me go a little bit back. Maybe. Yeah. This is the idea. I know that this vector will produce he and hit me with, right? So the idea is this. Why don't we use these vectors to represent he, me, hit me, and with, right? Represent this pi with this vector. Okay, is this a good idea? Because this one is going to produce pi, right? Why don't we use this vector to represent pi? Instead of word2vec, I can do that, right? Is this a good idea or bad idea? Can anybody tell me the positives and negatives of this idea?
Well, doesn't it depend on what came before it?
Say that again, Osama.
Doesn't it depend on what came before it? So
is it a
in
good thing or
another
bad thing?
context, it may be a bad, or it may be a mismatch in another context.
Yeah. So is it a good thing or bad thing?
I think it's a bad thing.
It's a good thing. Why? Because you don't want to represent pi as a single word. Pi has many different meanings, right? And I like to give a different vector for different meanings of it, right? So in this case, pi is just a food, maybe a food that can be thrown to somebody's face. Okay, so it is that meaning of pi. If I need to use pi in some other context, for example, pie chart pi, right? Its vector should be very, very different. So that's a good thing actually. So somebody came up with this idea. Let's not use word2vec, kind of representations. Those representations are good for coming up with a vector for the word itself without independent of the context. Let's develop this context-dependent vectors. And if you like to find the complex independent vector, just take the average of all the vectors of pi. That would be good enough for you. That was the idea, and it was the Elmo. Okay, Elmo representation. It used this idea on the LSTM networks, and later they came up. Then changed that idea, and they generalized it to the transformers. Transformer is the network that uses attention, and BERT is the one that uses Elmo idea on the transformer network. Okay, so BERT is this, and nowadays BERT is the number one word representation technique that everybody uses. It works very well for the Turkish. It works very well for the English. Okay, look at this one. This one uses the graph attention networks. Oh, okay, that's good. Okay, these are all language understanding, generative adversarial. Let me type this. visual attention. Visual attention. Oh, this is visual attention of humans, okay? I am talking about visual attention since this one. Okay. Learning and supervised video object attention through visual attention. So people are experimenting with this kind of stuff and initial results are coming back very, very nicely. Okay. Modulates reading. Okay. Let me try to see if there are very big ones. Did I? Okay. So in the visual attention word, visual transformer. Visual transformer. Okay, there is a even survey about visual transformer. Okay, so it is catching up. Everybody is doing this transformer stuff, and it is based on the attention. Okay, what did we do? Okay, attention is like that, and attention is basically dot product. I mean, there is nothing more to it. It just, you take the dot product between this representation and all the word representations, and it's going to tell you what part of the sentence you are paying attention to. Okay, and when you do this, see this one, alignment problem is automatically solved. This is automatically recovered. Okay, so when I am producing this he, what part of the sentence I am paying attention to, it is automatically produced, and this is automatically produced picture without giving any alignment, explicit alignment during the training phase, and the alignment is done that way. So when I produce this sentence out of this one, okay, I am paying my attention around here. So it is good in terms of explainability too. Okay, so there are many benefits of it. Okay, it's great. It significantly improves the machine translation performance, solves the bottleneck problem. It helps with the vanishing gradient problem. Why? Because it is feeding that information directly to the beginning of the network. It provides some interpretability like this one. Okay, and we get the alignment for free like this one, how much we are depending on it. Okay, and the network learns the alignment by itself. And with the transformer, they define the attention this way. Given a set of vector values and a vector query, so these are the vector values, these are vector query. Okay, you ask each of them, how much do you like me? How much do you like me? How much do you like me? Query and vector values. Okay, so given a set of vector values and a vector query, attention is a technique to compute a weighted sum of the values dependent on the query. Okay, weighted sum of the values dependent on the query. So you are basically querying the input sentence with this new word that I am producing. Okay, so we say that sometimes query attends to the values. So that's so they later, I mean, we expand this definition a little bit more. I mean, the values doesn't have to be single values. There are key parts of it. Key value query triplets. That's the more general definition of the attention. Okay, good. By the way, this attention, the attention that I showed you, this dot product only, is the simplest form of attention. Some of the other attention types, okay, some of the attention types, they introduce weights. This is the attention that I showed you. This one, the multiplicative attention, says that, okay, if you are going to compare this internal state with my inputs, there should be a matrix products between them, weight matrix. And you are supposed to learn this weight matrix. That's going to measure the attention. Okay, similarity. Okay, that's called the multiplicative attention. More general version of it is the additive attention. Okay, I multiply this as state with the current input. Like this is weight 1, weight 2, and add them, and I feed it through a nonlinear function. Okay, and these are the values, and well, I didn't talk about it, but so basically these two are adding more parameters to the system. So maybe we can learn generalized version of the attention. Okay, so once people learn that it is working good, so they start doing that kind of stuff. Okay, so that's the end of the machine translation lecture, and I stopped at this point of attention. So from this point on, if you are going to read about this, read about attention, read about transformer networks, not only for the neural machine translation or NLP, for any idea, any place that you are working on, attention is going to be your place to look at. Okay, that's it for for the makeup lecture. I'm going to stop here. If you have any questions, I can answer that. But in 5-10 minutes, we will start listening to our classmates' presentations. Again, how many people are there to make the presentation? At the beginning of the lecture, there were 5. Now we have 1, 2, 3, 4, 5. Where is Efkan? Efkan, aren't you? So you're not listening? Oh, okay. So I know Efkan is there. Who else? Niyazi, like you, as usual, he was not here at the beginning of the lecture. Ümit was not here either. Was he here? So I am expecting 3 more people, maybe. Okay, we will start at 3:30 and 10 minutes per person, and we can finish this up in maybe 50, 60, 70 minutes. Okay, good. I am going to check your submissions from the Teams page. Okay, and I'm going to get your reports from there, and I'm going to compare with your presentation. Okay, I'll see you in 10 minutes. 15:30 we will start our presentations.